Okay, so in this video, we're going to kind of start moving our conversation to bringing in circuits, okay? So we're going to start by talking about resistance and resistivity. So resistance, which we call R, is what we call the hindrance to the flow of charge, right? So this is going to, and you can see the word resist in there. So this word is going, these resistors or resistance is going to stop the flow of charge, right? Really, why does it stop it? So it can use it. So it can light a light bulb, it can charge your phone, it can charge your computer, you can turn on your video game systems, okay? But mathematically, we define resistance to be V over I. So V, right, remember, is our voltage. I is our current. And V, so this is in V, so in volts, current is in amps. So a resistance, right, is 1 volt per amp, which we call an ohm, right? And so this is the capital omega, right? The Greek letter omega. It's the horseshoe-looking symbol, right? So resistance is measured in ohms, which is, again, I said is the capital omega, and V, again, is the voltage from the source, which we abbreviate V. So now what happens is the conductor whose function in a circuit is to provide a specified resistance is what we call a resistor. Again, if you're interested in computers, these are like a lot of those little things on the motherboard or on circuit boards. Okay, so on the circuit board, you're gonna have resistors, you're gonna have capacitors. Okay, and we're gonna talk about RC circuits later, but you know they each serve their purpose on the motherboard. Okay, now resistivity, which is given the symbol rho, is a measure of the resisting power of a specified material to the flow of an electric current. All right, so this basically tells you how much is it going to resist. So as opposed to this being a property of the conductor, it is actually a property of the material. So the conductors are going to be made of a metal, right, or a material. The resistance is the property of that conductor, right? But the resistivity is a property of the material. And you can look right here in this little chart that I've included, right? These are just some sample resistivities, right? Again, on the test, if they're using this quantity, if you don't have to solve for it, they're probably going to give it to you. There is no chart on the AP Physics C exam that has resistivity as materials and temperature coefficients and so forth, okay? Now, mathematically, we simply find it of E over J, right? So the electric field divided by J, which is that current density, okay? And resistivity is measured, and you saw it in the chart, is what we call an ohm meter, or an ohm meter, right? If you look at this chart right here, it's an ohm times meter, all right? Now, we can determine an unknown resistance by calculating the known resistivity. So we don't know the resistance of a conductor, but we do know the material, which means we can find the resistivity. And what they actually do is they look at it in terms of a wire, right? And so the resistance of a conducting wire of length L and uniform cross-section, I forgot to write the A in there, okay, is simply R is equal to rho L over A, right? With rho being the resistivity, L being the length of the wire, and A, you see right here, is the cross-sectional area, right? Now, unless otherwise noted, most wires have a cross-sectional area of a circle, okay? But what you actually see in this example problem, it's not a circle, it's a rectangular prism or a rectangular block, okay? So, and this shows you how the length does play into it, because when we do this example problem, we're going to look at it when you look at the square ends versus the rectangular sides, and the lengths are going to change because, right, So let's just dive in this, right? So it's a rectangular block of iron, has dimensions of 1.2 by 1.2 by 15 centimeters. A potential difference is applied to the block between the parallel sides in such a way that those sides are equipotential surfaces. What is the resistance of the block of the two parallel sides are the square ends, right, which have dimensions of 1.2 by 1.2, or the rectangular sides. All right, so here's our block. And so this is 1.2 by 1.2 by 15. So they're saying for part A, we're going to look at the resistance if we connect wires to that side, or to the squares, and then part B, if we connect them to the rectangles. So the thing that you see is when we do our L, right, so our cross-sectional area for part A is going to be 0.12 by 0.12, okay, which ends up being 0.0144. Let me just double check that because I plugged it all into the equation. So I'm going to grab my phone. I can't seem to find my calculator right now. But again, phones have built-in calculators. So 0.012 times 0.012. I forgot a zero. So if I just erase that decimal point, and I go zero, I'll just trace a little bit more, 0.0014. Okay. So now that's what I'm going to plug in. So I'm going to use my resistance equation. So rho L over A. The resistivity of iron is 9.68 times 10 to the negative 8 ohm meters. The length that we're going to pass this through is 0.15, and our cross-sectional area is that number that we just found, the 0.00014. And so what is the resistance here? It's going to be 1.01 times 10 to the negative 4th ohms. Okay. And so when you have wires, it does depend on the length of that wire. And so now let's do, when we do it through the rectangular sides. So the rectangular sides are going to have a dimensions of 0.15, 4. So it should be a 5 by 0.012. Okay. And again, I plugged it all into the calculator. And so we're going to say 0.0018 square meters. And again, this is square meters. So I use my resistance equals rho L over A. The resistivity doesn't change, so it's 9.68 times 10 to the negative 8. Now my length changes because now it's going to be, right, the length that we're passing through is one of the sides of the squared, and 0.0018. And so when you turn it to be passing through the rectangular side, note that the resistance does change, and changes considerably. So 6.45 times 10 to the negative 7th ohms. And that looks like a 2, but it's actually a 7. Okay. And so now from here on out, again, we're going to keep building on circuits.